Ratio Test, narrated by Dr. Rebecca Swanson, Colorado School of Mines. In this video, we are going to learn about the ratio test, why it works, and how to use it to determine the convergence or divergence of a particular series. First, let's take a look at the result itself. For the ratio test, we're going to start with a series, and in version 1, we're going to have an extra assumption. We're going to assume that the terms are positive. We're going to look at the limit L as a limit as n goes to infinity of an plus 1 over an. So this is where our ratio comes in. We're taking the ratio of consecutive terms in our original sequence. If that ratio limit is less than 1, our series converges. If L is bigger than 1, the series diverges. And if we get a limit where L equals 1, the test is inconclusive and we'll have to try something else. So the first question that we're going to answer is, why does this test even work? Let's start out by looking at this limit as n goes to infinity of an plus 1 over a sub n equaling L. Whenever something limits to a number L, what that means is that for large values of n, we'll think of n bigger than or equal to capital N, the terms in that sequence have to be really close to L. So these terms are approximately L. So in particular, starting at that capital Nth term, the large N, a sub capital N plus 1 over a sub n is approximately L, which means that a sub n plus 1 is approximately a constant multiple L of a sub n. The next term in our sequence must also be approximately L. And we get a similar relationship. an plus 2 is approximately L an plus 1. We can substitute this and get that an plus 2 is approximately L squared an. Let's do one more. The next term is an plus 3 over an plus 2. So we get an plus 3 is approximately L times an plus 2, but an plus 2 is approximately L squared an. So this is approximately L cubed an. This pattern continues. So let's think about what this means for the rest of our series. The sum from k equals 1 to infinity a sub k is a1 plus a2 plus a3, etc., up to the n minus 1 term, and then we get the nth term, the n plus 1 term, the n plus 2 term, etc. Now the first n minus 1 terms are the partial sum s sub n minus 1. And then we still have the remaining terms. Now if we utilize our work over here, well, we have a sub n, then we have L a sub n, L squared a sub n, L cubed a sub n, and so on. And again, this is an approximately because we had approximately's over here. S sub n minus 1 is a number that we can calculate. It's a sum of finitely many terms. Let's focus on the rest of our series. This is really just a geometric series. We have a number plus a geometric series. In our geometric series, a is the nth term in our original sequence. R is L, and we know that if L is less than 1, the series is going to converge. If L is greater than 1, we know it's going to diverge by the geometric series test. Now the question we want to answer is, what happens when L is equal to 1? In this case, the test we're told is inconclusive. And that really has to do with this approximately symbol. Because if we have an approximately 1 for our limit L, then the actual values might be above or below 1, meaning we might actually be in one of the first two cases, but we don't know which. And so that's why we have to say inconclusive. It's really connected to that approximation. Before we move on to doing an example of using the ratio test to determine convergence or divergence, I do want to mention that we can actually get a nicer version of the test. So here's our full version of the ratio test. We're going to eliminate the requirement that our terms are positive, and we're going to add some absolute values to our ratios. And then this test still works. And what's really nice is that we don't have to worry about terms being positive anymore. Now the reasoning is mostly the same but requires a few results we don't have yet, so we will omit the proof of the full version at this time. But again, what's nice here is now there's little to check regarding necessary conditions to use the test. All we have to do is take the limit of ratios. So here's an example. Let's say we want to determine whether the sum from k equals 1 to infinity of 1 over k factorial converges or diverges. We're going to use the ratio test, so we should first identify our a sub n, 1 over n factorial, and then we have to take our limit. L is going to be the limit as n goes to infinity of absolute value an plus 1 over an. An plus 1 is 1 over n plus 1 factorial. An is 1 over n factorial. I can now at this step notice that all my terms are positive, which means the absolute value signs are unnecessary. And I can also write my fraction division as multiplication by the reciprocal. Now let's look at this n plus 1 factorial term. I'll kind of move off to the side here. That's equal to n plus 1 times n minus 1, all the way down to 1. But notice these terms comprise n factorial. And so I actually get that n plus 1 factorial is n plus 1 times n factorial. Cancel those terms, and I get a limit of 0. So I can say since L is less than 0, our series converges by the ratio test. So to close, at this point, you should recognize the ratio test as a method for determining convergence or divergence, and you should be able to try to apply it to at least a simple series example.